This will help you get started on the Winch Lab. So it's called the Winch Lab Mechanical System Efficiency. So this idea is efficiency. We're thinking about how much is wasted or how much is used to what we want. And this is a mechanical system because it's a winch, and winch are used to lift things up. So here's our introduction. Everything in yellow is important, and we would copy this down into your notebook if you're doing it on paper, or if you're doing it just by filling out this sheet as a PDF, then you can just make sure that these are things that you really understand. So, introduction. Energy cannot be created or destroyed, but energy can be converted from one form to another. This is an important idea that we're going to revisit. By design, an engineer creates an energy conversion system to change an input energy form into a desired output energy form. However, within a conversion system, input energy can be changed into less desirable forms of energy. Less desirable forms of energy conversion can occur due to resistance and friction, resulting in conversion to thermal energy, heat. Energies strive to decrease undesirable energy conversions within a system or energy losses by planning with system efficiency in mind. Efficiency is the ratio of desired output energy compared to input energy. And for us, when we do this equation here, we're going to look at the power out and the power in. So power is work divided by time. If we do the power out in the same time as the power in, or this is the same as comparing the energy in to the energy out. So we're going to use this formula. A common form of energy occurs today through electromagnetic induction in a power plant. Electromagnetic induction transfers mechanical forces and motion energy into electrical energy. The electrical energy is then transmitted to industry and homes to be used in a variety of ways, many of which include conversion back to mechanical energy. An electric motor converts electrical energy into mechanical energy. A winch winds up a rope or string. A winch can be used to lift or pull objects. So here, this is what we're going to use. And we can actually go to the winch intro, and you can see some of the pictures of things that people do. So here's a winch that the guy has an electric motor on that winds this up and pulls in a boat. Another example here showing how it has a remote control, and so this electric motor can be controlled to wind up the boat remotely. Here's another winch in which steel cable is used to wind this up, and in this case here, that steel cable is wound up to lift something underground. Here's another example of a winch. Electric motor winds up this cable. Here's one where they used a winch to rescue a cat that fell down a well, some sort of, I don't know, it was a leopard. You can also lift elephants with winches. They can be very strong. Here's an example. If you're a hunter, people shoot their deer and then they want to lift it up on their truck. Here's a mechanical winch. This one's operated by hand. And another one here, fishing. There's an electric winch, catches some fish. Winches can be used to pull things up mountains. In this case, this tree chopper chops down trees. That gets up the steep mountain by pulling itself. Here's a winch that you might see on a street. They pull up this winch. Here's a winch run by an electric motor here, winds this up and lifts things out from under the street in the manhole. There's a winch on a Jeep. This winch is an electric motor right here, and this electric motor winds up this cable, pulled the Jeep out of the mud. Here's one. This video is kind of funny. They have a winch that pulls a skier. We can watch this video real quick. And you can see how this winch is used to pull a water skier across. So they hook this up on their Jeep, wind it up, and then they use that winch to pull a water skier all the way across the lake. So here it is, winding it up and pulling this water skier. You can water ski without a boat. In our lab today, we're going to use this winch that is a Vex winch. We built these last year. We used them in class, and here this winch is lifting 10 pounds. We're going to use this power supply where it measures voltage and also current, and to see how much power we're putting into the winch, because remember, electrical power is voltage times current. So that's what we're going to use on this Winch Lab today. So we built this Winch Lab in class. We use these parts, put them together, put an electric motor on. We had a little gearbox. The electric motor would turn the small gear, which would turn the bigger gear, and the bigger gear would wind up the rope. So there's a gear ratio here. And then we used a permanent marker to mark the rope. And then we have the stopwatch. So what we're going to do is we're going to set up this circuit. We're going to set up an electrical circuit with this winch. You can see here, we're supposed to draw a circuit diagram showing what's connected. So if we thought about this here, what would this look like if we we drew on here, if we want to use these symbols, well, we would have a voltage source. And then that voltage source, we have a voltmeter that's going to be using it and a current meter. So the current meter goes in the circuit. And then this circuit's going to go up to this electrical motor symbol. So I'll put an M here. And then we're going to go back. We have a switch. So we'll put that in there. And that switches, there's the button that we use as a switch. And then we go back to our battery. And we're also measuring the voltage that's being put out by the meter. So that voltage we can put it here, and that's connected to each side of the power supply. So we know the voltage and current. Since there's only one resistance in here, this voltage will be the same as the voltage on the motor. So we can look at that one. The voltage into the motors is going to be the same as the voltage out in the power supply. And so that would be that one there. Drawing the setup as a picture, it's going to look something like this. And you guys can just use that picture to do those ones. Okay, and now we're going to look at our data. So the first one is we got 5 pounds to be lifted in grams. So they wanted to be in grams. An easy way to do this is with Google. You guys could just look at a new thing here. We want to know 5 pounds in grams. And they give it to us right here, 2267.9, so 2268. So we can put that in right away. So I would put in here 2268. So 2268. Then we got to convert that to newtons. Well, 2268, we got to first go to kilograms. So if we have 2,268 grams, I'm going to multiply that by 1 kilogram is the same thing as 1,000 grams, because kilo means 1,000. Okay, and then we have our old, once we're in kilograms, we can multiply by 9.81 or 9.8 if you want to be less decimals, and this is newtons per meter squared. And newtons, kilograms, I'm sorry, meters per second squared, which basically for us just is going to turn this into newtons per kilogram. So we can leave that there. And when we do that math, that should come out. We can also do it again with 10 pounds. So we can use in decimals. Also, if you just wanted to go 5 pounds in newtons, to check this out, they give us a force here that's not too bad. So we could just put this straight in here, 22.24. So we'll go back here. And we could just put that answer in here as 22.24 newtons. Again, we got to do the same thing for 10 pounds. If it's twice as heavy, it's going to be twice as many newtons. So we can put that one in there like that. All right, so when we finished up here, we were at 5 pounds was 22.24 newtons. And that would make 10 pounds twice as much, or 44.48 newtons. All right, so that was that part there. And now what we do next in this lab is we'd attach that weight, and they made marks 15 centimeters down from the second point. And so that's what we're going to lift. So if we look here, that we're going to lift this thing 15 centimeters. How many meters is that? Well, this is something that you should remember. 15 centimeters is, we got to convert to meters. So centimeter goes on the bottom, meters goes on top, and 1 meter is the same as 100 centimeters. So that's something you should definitely remember, is this conversion factor. That's going to show up on the final. And if we divide by 100, you can see the units cancel out. We're going to move the decimal over 2 places, so 0.15 meters. So that's the answer for number 2. That's the distance we're listing it. And then what happened is we would use this bump switch, we'd push down the button, and we'd start lifting it. And we need to figure out the weight, how many newtons it was, and then we need the voltage and current, and how long it took to lift it. So when we look at this 5 pound, we can watch the video here if this is what actually happened. It's set at 7.5 volts, and right now it's off, so there's no current. But as we hit play here, you can see that 7.5 volts, and then it's up to 0.24, 0.23, 0.24, and it lifted up, and we lifted up 1 space, and that was how long it took. And if we look at the timestamp down here, oops, if we look at the timestamp right here, on here I hit play. Oops, wrong one. So I gotta start this over. All right, so they started at about 3 seconds and they ended it here at about 8 seconds. And so if we look on how much time that was, we could measure it with the video and we could think about how long that took. So I have here, when I looked at it more carefully with a stopwatch, that at 5 pounds, it took 5.8 seconds, so just under 6 seconds. So we'll go back here to our lab, and I have here that when we lifted the 5 pounds, oops, get out of here. So when we lifted the 5 pounds, this was 22.24 newtons. The voltage was 7.5, and the current here bounced around, but a 0.24 was a good estimate, and the time it took to do that was 5.8 seconds. Okay, so that's our data for the first part. And then we would unwind the winch and we would do that again for the second part. And so we can watch that video here to see how much time that took to lift it up. So here again, the voltage was at 7.5. And when we hit play, we can see it starts pushing at 2 seconds. Here we're taking more current, 0.3233, and it took right about the same amount of time. So that's interesting. Even with double the weight, 10 pounds instead of 5 pounds, it still took the same amount of time. However, it did take more power. So we could write these in here too. Now that we're at 10 pounds, that was double it, so that was 44.48 newtons. And the voltage was still 7.5. And now the current here bounced around a little bit more, but it's about 0.31. And the time it took was the same. It did slow down at all. So that kind of tells us that the motor was plenty strong to be able to lift the weight, because it didn't take any longer, but it still did take time to wind it all up. All right, so those are datas, and now we can go down to what do we do next? So now the next here, we got to find the work. So work involves the amount of force it takes to lift something. So we already know this one because we know the newtons, that's the force, and then we got multiplied by the distance, and we know that one too because we measured that as 0.15 meters. So here the force was 22.24 times 0.15. And for the second one, we had twice the weight, 44.48, also times 0.15. So if we put those decimals, if we use decimals to do those work, I'll open another window here with our favorite decimals. All right. And maybe I will pull this off as a second window, just to make it easier to pound these numbers in here. There we go. So if we go back here, we have 22.24 times 1.5. So 22.24 times 1.5, 33.36. And again, this is in joules because it's work. And then we're going to do the same thing, but 44.48. Oops. Wrong decimals. Sorry. There it is. We got 44.48 times 33.36 times 1. Whoa, bad answer here. Not 1.5, 0.15. Whew. That would throw us off our decimals here. So 3.36 and 0.15 here, 6.672. So let's change that here. 3.36. Where's my eraser? That's the highlighter. All right. And then we got to do the other one. It's going to be, remember here, it was 6.672. All right, so that's how much work we did. And here we did it in 3 decimal places, just like the answers told us. Okay, so if we lift twice the amount of weight, we get twice the amount of work done. And now we can go down here to close this out, and we'll look at the power. All right, so power involves the time, force, and distance. 2 winches, one slow and one fast, do the same amount of work to lift a given weight through a given distance because they use the same force to lift and cover the same distance. So same work if you're same weight, same distance. Time is not a factor when calculating the amount of work done. So it doesn't matter if you go fast or slow when you're looking about work. However, power does matter. But to cover the distance faster, the faster winch uses more power. And we'd say more power because it's doing the work faster. So use the formula below to calculate the output power of the system in watts. All right, and we'll put our work in here. So the power, if I remember what it was 3.336 for weight 1. 3.336, and we divide by 5.8 seconds because that's how long it took. And if we put that into decimals, we get 3.336 divided by 5.8. And that gives us 0.575 watts. 0.575. Now this would be joules per second because it's 3.336 joules in 5.8 seconds. But joules per second is the same thing as a watt. All right, so that's how we do that one. I'll let you guys do the work for weight number 2. The same thing, the work to lift weight number 2 divided by the time to lift work number 2. And then we can go here to calculating the power in. So the power out was the winch lifting the weight. But now the power in was how much electricity it got. So if we look at weight 1, the current was 0.24. Remember, this is power equals current times voltage. So 0.24 is the current, and the voltage was 7.5. And if we look that up into decimals, we get here 0.24 times 7.5, and that gives us electrical power of 1.8 watts. So we'll put that back in here, 1.8 watts. All right, now notice here that we had more power in than power out. 1.8 watts versus our other answer was 0.57. So we had more power coming in than power going out. So this is going to be interesting for us. All right, again here, I'll let you guys do number 2. If I can get out of this screen. All right, so you guys can do weight number 2 there. And then we can jump to what the efficiency is. So efficiency compares the power out divided by the power in, and then we multiply by 100%. So for the first weight, we had our power out, if we remember, was 0.575. So 0.575. And then we had to divide by the power in, which was 1.8. And then we're going to multiply the whole thing by 100. So that's our answer. So I'll put this in here, 0.575 divided by 1.8 times 100. And that gave us an answer of 31.94%. All right, I'll let you guys do number 2. And in the same way, once you get those calculations done, then you should be able to answer the conclusion questions. And they were, list and describe 3 factors that reduce efficiency in the winch system. Well, the directions said friction, changing energy into unwanted forms is the key thing. So if we look at what happened here, when we play the video, there's definitely noise. So you guys could play those videos and listen to it. Also, when we look at the winch, any places there's friction. So where could there be friction being in this? Well, definitely the axles were rubbing when they wound it up. There could also be some friction between the gear teeth. And also the motors are quite loud. There could be a lot of friction inside here. And as you do this lab, if we're doing it in class and felt the motor was getting hot. And so not only was the motor getting hot, but also the gears and the axles could be warming up as they rub against each other. And it made a lot of noise. So those were the 3 things that I would go with for the conclusion here. Is what 3 things they have? Well, they definitely had 3 factors: friction, and there's friction 2 places. There's friction inside the motor because it made noise and got hot. There's also friction between the axles and gears, and it also made noise. Noise is unwanted, and so that would be a waste of energy, and that would reduce the efficiency. So I'll let you guys just answer number 11. Describe one strategy for making the system even more efficient. And number 12, explain 2 or more reasons why automotive engineers are concerned with eliminating inefficiencies from vehicles. And then once you do those, you should be able to turn in. It shouldn't be too bad. So the video here is 20 minutes. Probably take you another 10 minutes to finish it up. So it should be good, about at least 30, 45 minutes. It should be a good assignment.